My pleasure to announce the first talk of today. Professor Sankaranarayanan from the University of Hyderabad will speak about mean value theorems of zeta S on certain vertical lines. So please.
Okay, thank you, Stefan. First of all, my sincere thanks to the organizers for inviting me to give a talk in this nice occasion. And of course, Professor Balasubramanian is my second teacher, so to say. After Professor Ramachandra, I have high regards for him and my best wishes to him and his family in this important event. And I wish him a healthy, peaceful, long life. And let me start my talk now. By the way, I'm really sorry that I could not participate in the yesterday's celebration event. Unfortunately, I had to do a lot of work here. I had already informed the people. I hope you will understand. Okay. So we start with the symmetry function dkx, which is symmetry function related to dkn. Dkn is the number of ways of expressing n as a product of k factors. One knows that this symmetry function satisfies certain asymptotic formula where ekx is the error term and pk is a polynomial of degree k minus 1. If one defines beta k to be the least number such that this mean square error term is O of x power 2 beta k plus epsilon for every positive epsilon, then the study of beta k naturally leads to studying higher moments of the Riemann theta function on certain lines. In this connection, to study beta 4 and beta 5, Heath Brown showed that the 8th power moment of the Riemann theta function on the line 5 over 8 is less than t power t times log t power 38, and the 10th power moment on the line 11 over 20 as t power 3 by 2 log t power 52 for large t. Because of the functional equation of the Riemann theta function, from these two estimates, one deduces that beta 4 is less than or equal to 3 over 8 and beta 5 is less than or equal to 9 over 20. And it is known that beta k is greater than or equal to k minus 1 over 2k for k equal to 2, 3, etc. So this settles the question for beta 4, which is exactly equal to 3 over 8. So let Bn denote the number of isomorphism classes of abelian groups of order n. The arithmetic function Bn is multiplicative. And if you write the generating function for this multiplicative function, it's the product of Riemann zeta function at different arguments. And you have such an expression. If you write the counting function with the weight Bn as Ax, one knows that Ax satisfies such an asymptotic formula with this error term, with this counting function. One knows that this error term in this situation is less than x power 140 plus epsilon. On the other hand, the following result is due to Ramachandran and Balasubramanian, which tells you the square integral of the error term is omega of y power 4th over log y, which tells you that as an omega estimate lambda x satisfies bigger than x power 1/6 some log power whatever. On the other hand, if you ask the upper bound for this square integral, Heath Brown succeeded in showing that this satisfies roughly the expected order apart from the log factor. So this square integral, he showed that y power 4/3 log y power 18 for large y. Earlier works related to this inequality were done by Veach and so on. So anyway, well, So there are some related works by Iwich, Motohashi, and so on. Judila, Matsumoto. Several people have done mean value theorems. So I just make their names here to know. And let me point out here, Condry and Bonner presented some nice heuristic arguments to formulate several important conjectures. Using these conjectures, they obtained some highly interesting results. We quote one of their conjectures here, which is very much relevant here. Let me call dkys to be this Dirichlet polynomial. Then the first conjecture tells you that for every positive integer k, one has this 2k to the power mean of the Riemann zeta function on the half line behaves almost like the 2k to the power mean of this Dirichlet polynomial, where the product of these parameters x and y should satisfy xy equal to t over 2 pi power k with xy is bigger than or equal to half, or y is bigger than t over 2 pi power k if x equal to 0. From the Montgomery One Theorem, for instance, you have such an asymptotic relation, one actually obtains the first square integral for this Dirichlet polynomial. The line have to be asymptotic to this order, and the ak is explicitly one can write, and this is true for y less than t. For higher moments, at least one of x and y must be significantly larger. In our situation, one expects that conjecture 2 for p greater than or equal to 10, and for every integer k greater than or equal to 2, the inequality, namely the 2k to the power mean on these lines, is less than t times log t power ak, where ak is some positive constant depending on k. Of course, one knows that conjecture 2 is true for k equal to 2, 3, and 4 due to Hardy, Kramer, and Heath-Brown respectively. For k greater than or equal to 5, the problem is still open. The aim of this talk is to exhibit the following. What we want to show is that from the Heath-Brown's result, for example, all that we improve only the exponent of log t. That should be noted very carefully. Of course, additional factor of double log t is coming into the picture. And as far as theorem 2 and 3 are concerned, even 4 also concerned, if at all any improvement you want to make, only the improvement can be done only in the power of log. Because the omega theorem will tell you that at least you can show that greater than t. So improvement can happen only in the exponent of log t. This is just a remark. Okay, I use standard notations, so let me just push it down. And I use the gamma function, some bound in any fixed vertical strip. And one knows that a Riemann zeta function satisfies a functional equation of this form, where this conversion factor is of order, upper and lower order of the similar nature. And I use this following inequality many times here, which tells you the following. Whenever you have the ai non-negative numbers and alpha i non-negative numbers with the summation alpha i equal to 1, then the inequality minimum of these L quantities is always less than or equal to the product of these L quantities with the exponents are chosen to be alpha 1, alpha 2, alpha L, with summation alpha equal to 1. This is a beautiful inequality. Of course, if A1, A2, AL are independent, then this inequality is real. Of course, this inequality can be proved by induction, for example. The point here is that we will be finding out several upper bounds for the same quantity, introducing some parameters. We don't know how the parameters will behave, but by the correct choice of the exponents alpha 1, alpha 2, alpha L, we will try to kill those parameters so that whatever we want, we would like to achieve. This is the main motivation for using this inequality. And another inequality which plenty of times used, this one. So the first lemma is the following. This is nothing but the approximate functional equation with one expects this 10th power moment of this error term is controllable. Controllable means it's of smaller order than our client, whatever the theorem. Say, for example, if you take sigma equal to 11 over 20, then you expect that this should be less than t power 3 over 2, log t power something, log t power something. This is what. The next one is something like complex function theoretic lemma, which is well known, which tells you that the center of an arithmetic function, the value of an arithmetic function at the center in absolute value is controlled by certain quantity. So, provided the maximum is less than or equal to h, etc. This I will be using somewhere. The next one is, this is well known, this is called the Montgomery One Theorem. This tells you that given a Dirichlet polynomial of length n, you have such an asymptotic formula, but the important point here is that this error term O of n is very important for us because after all you expect improvement in the log power. So if you lose any log power here, that will have implication in the final estimations. So it is better to use the best. This is one thing. Another one is that suppose you have a set S double star of complex numbers with this following property. And here, absolute value of imaginary part of S minus S dash is greater than or equal to 1. That means that these 2 points are well spaced. So if you want to count the number of well spaced points from the set S double star with the Dirichlet polynomial S of S in absolute value is large. This is what you would like to have. I use this is the version of Ramachandra, for example. I use this, even though it has 4 terms. One can handle. And here, the S of S is the Dirichlet polynomial. This one and G is nothing but the sum. Okay. The next one I use is the 12th power moment of the Riemann zeta function, and this estimate is due to Riemann. The next one is that the Riemann zeta function, if you tamper the coefficient 1 by e power minus n over x power h, then still for this Dirichlet series also the 12th power moment behaves almost similar like Heath-Brown's bound with the loss of double log t power 12, which is anyway immaterial for us as far as the estimate is concerned in our theorems. Okay, this for instance, this can be shown using the 2 variable Gabriel's convexity and maybe Holder inequality in a suitable way, etc. I'll just skip this one. So now let me concentrate my my talk on the first theorem, that is on line 11/20. So in principle, you need to deal with the two Dirichlet polynomial of length root t. So we consider the dyadic sums in each one. And what one does here is that you introduce a balancing factor, L power 1/20, so that if you combine this balancing factor with the first one, and if you combine this balancing factor with the second sum, both behave almost similarly, so that you don't have any problem with analysis. So this balancing factor, of course, these are all original ideas due to Heath Brown. So now what one does is that we replace this integral by a sum over well-spaced points Tn in this interval, satisfying mod Tm minus Tn greater than or equal to 1 for m not equal to. So from the approximate functional equation with whatever you have, one observes here that zeta of 11/20 plus it is less than log t maximum of this discrete sum L power minus 1/20, and this dyadic length L is less than or equal to C t power half. So now what one observes here is that the integral under consideration, what we want to have, which is less than log t power 10 L power minus half summation this discrete sum power 10 whatever. If one denotes nu to be the number of well-spaced points Tn for each u where u runs over powers of 2, for which this sum absolute value of S of L Tn lies between u and tu, then clearly one observes that the integral under question is less than log t power 11 L power minus half nu u power 10. Here these two parameters L should satisfy L less than root t, and the parameter u should satisfy bounded below and it is bounded above by L power 1. The next step is that one observes t lies between t/2 and t, and the conversion factor of the Riemann zeta function is behaving like t power 1/2 minus sigma. And what we do, we take these two sums separately, and one notices that mod S1 plus S2 satisfies this inequality, so that if you call N1U pertains to the number of well-spaced points Tn, for which mod S1 lies between u/2 and u, and the N2U pertains to the number of well-spaced points Tn, for which mod S2 lies between u/2 and u respectively, then this implies that for every well-spaced point T counted in Nu, there is a well-spaced point T need not be the same being counted either in N1U or N2U, and thus Nu is less than or equal to N1U plus N2. It is enough to analyze N1U below. N2U is similar. So one uses the Perron's formula, and you have the cubed power of S1. You can move the line of integration, etc., and then one observes S1 cube satisfies such an integral, and this thing you can use Holder's inequality in a suitable way. Indeed, that gives you that u power 12 N1U is less than this 12th power discrete sum. And this is according to the 12th power moment for Fs, the tampering L function. We have such a bound. So this tells you a bound for N1U. This inequality, of course, in terms of U and T, etc. Similarly, if you use the 4th power mean of the sum, you can use, for example, Montgomery One, and you can obtain such a bound that will give you another bound for N1U in terms of U and T. And And the next step is to use Ramachandras counting of well-spaced points in a given set. That will give you essentially another bound for N1U in terms of L, U, etc. So you have in principle 3 bounds for NU. For N2U also you can have similar bounds. So essentially NU you have 3 bounds. One from the 4th power, another one from the counting of well-spaced points for the given set. Another one is the 12th power mean for the tempering L series and whatever it is. So you have 3 bounds. You want to have a uniform minimal bound for NU. So what one does here, of course, in the Ramachandras lemma, you have 4 terms. You don't know which one is maximum. So one by one, 4 cases come into the picture. If M start with the maximum of all these 4 quantities, you take first the maximum to be L square e power minus 4 log t cube. And then what one does, of course, you have 3 bounds at your disposal. You can select any of them or all of them, something like that. And only thing is that you have to choose the exponent alpha I suitably in such a way that exactly this u power minus 10 L power half come into the picture, so that will get cancelled when you estimate IT. So this is what one does here. In the first case, when the M star is L square e power minus 4 log t cube, you choose alpha, one alpha to be 1/4, another one is 3/4. Precisely this gives. And if you fit in the previous estimate for IT, essentially that will lead to IT to be t power 3/2 log t power 25.25 double log t power 9. And case 2, in a similar fashion being done, of course, you are choosing the bounds suitably, then your bounds and the choice of exponents here 1, 4, 1, 4, and 1/2. You can see that, and essentially here also it leads to IT to be less than t power 3/2 log t power 24. And the third case, t power epsilon. Maximum is t power epsilon in those 4 terms. Then one observes here that the 10th power mean of this Dirichlet polynomial with shorter length, for example, that is controlled by t power 3/2, and the cognated sum is also of similar order. So in the dyadic split, actually the L can be assumed now to be bigger than t power 1/10. So now if U is less than something, again you show that IT is of desired order. And if U is bigger than this quantity, again you show that it is of desired order. Of course, here again I use the inequality, whatever I mentioned here. So again, it gives you the desired order. So the last case in this one is M star to be this one. Here, of course, you notice is these 2 bounds can be used, and the exponent to be 1/2, 1/2. So again, it leads to whatever you want. So this precisely completes the first part of the first theorem. The second and third theorem related to the lines 5/8 and 2/3 of the 8th power moment and the 6th power moment respectively follow the similar arguments. So I don't go into those details. Well, yes, I have given some details anyway. Okay, now let us come to the square integral of the direct term related to the abelian group problem. Already from the work of Lewis, one observes here that this square integral of the direct term is less than y power 4/3 log y square maximum of some quantity that IT star is nothing but this square integral where the integrand, if you see, there are 5 factors. With sigma is nothing but 1 over 6 plus 1 over log y is sufficiently large. One observes here that the following inequality, 2ab is less than or equal to a square plus b square, true for a and b non-negative. Then using this inequality, one observes that the integral it star actually less than or equal to maximum of these two integrals, where jt star is nothing but this guy and jt star prime is nothing but this guy, and both are of similar nature, so we will just concentrate on jt star. Here, of course, the situation becomes somewhat complicated because you have 3 factors, so you have to introduce 3 sums, S3 star, S4 star, S5 star, and sigma is equal to 1 over 6. So regarding S3 star, you don't need to introduce the balancing factor. On the other hand, related to S4 star and S5 star, with these parameters m and n, you need to introduce a balancing factor as n power 1/6 here and here n power 1/3. With this, one argues in a similar fashion, and indeed, if you count the number of well-spaced points, essentially this will tell you that your jt star is less than this guy with this one. So if you call, so one can classify the well-spaced points Tn in such a way that mod S3 star lies between U and 2U, S4 star lies between V and 2V, S5 star lies between W and 2W, in which relevant sums lie. Here UVW runs over powers of 2 and they should satisfy these inequalities. And if you call n star UVW to be the number of well-spaced points Tn for each triplet UVW, then it follows that jt star is nothing but this quantity. So we need to estimate n star UVW in a particular fashion. This is what we do. Of course, these parameters L, M, N, they satisfy less than t power 1. The next step here, of course, what we do for each one, for S3 you have 2 sums, for S4 another 2 sums, and S5 you have another 2 sums. So one observes here that nj star UVW for j equal to 1, 2, 8, etc., being the number of well-spaced points Tn for each triplet, with S3 1 star lies between U by 2 to U, etc., etc. There will be 8 cases actually in this part. Yes. Then one observes that the n star UVW is nothing but less than or equal to sigma j equal to 1 to 8 nj star. So proceeding as before, for any integer k greater than or equal to 1, one has, using the 2kth power moment general, one has such an estimation for n star UVW as with involving L and U here. For another one, you have M and V. Another one is N and W. This is one set of bounds. And if you apply the well-spaced points lemma, you will have another 3 bounds for n star UVW. These are the 3. And of course, if you apply the 12th power moment for the tempering this one, then another 3 bounds you have. Now you have to play around with all this. This is what one tries to do. But here one observes that one can restrict ourselves to m less than or equal to m. Otherwise, anyway, you have such an inequality. And n less than or equal to m case, what we do, we split into 4 cases, like 1 less than or equal to m less than or equal to t power 1/4, 1 less than or equal to m less than or equal to t power 1/4, n less than or equal to m, of course. And the second case is up to t power half, here m up to t power half. The third case is 1 to t power 1/16, then n here, and m is from t power 1/4 to t power 1/2, and the rest. All these four cases will adjust the possibilities. So now systematically one has to argue when k equal to 2, k equal to 4, etc. Of course, I am at my disposal to use the exponents and all these bounds wherever I want. Use with the suitable exponent and observing the fact that n less than or equal to m in my case, and etc. And then in each one of the cases, I derive the upper estimate for n star UVW. So, yes. So precisely this is what is being done here. Yes. So finally, what one observes is that essentially it gives you. Now you see, in one case you have to argue whenever you use number of well-spaced points counting business, you have to argue 4 cases there. Again, one uses that point, and then using the exponents appropriately, using all these available bounds, and then you obtain bound whatever you want from n star UVW. Finally, if you fit in this n star UVW, okay, this is the bound what you want, and IT star is already you have shown some bound involving n star UVW. If you fit into that this bound exactly, this m power 2/3, n power 4/3, u power -2, v power -4, w power -4, these factors get cancelled precisely, and then you are left with whatever you want. I think I am through. Hello.
Okay. Yeah, thank you very much for the interesting talk. Are there any questions? I don't see any questions. Okay, if there are no questions, then let's the speaker again. Okay.
Thank you very much.